Hi, welcome along to this third video on integration for the P1 syllabus. In this video we're going to be dealing with areas and definite integrals. In the previous videos we were learning integration. Really what we were doing is finding antiderivatives. And so here we're really getting into the thing that differentiation is all about, finding areas underneath curves. The previous video was about the mechanics of the algebra of how you find an antiderivative. So you also might have called that indefinite integration as well. So here is the fundamental theorem of calculus. It sounds pretty grand, and it is. It's the connection between differentiation and integration. It's a little bit tricky to understand, but when I show you a few examples you'll get the hang of it. What this says is that to find the area under the curve we need a different function, this big F. So to find the area under this curve f of x, between b and a, we go f of b minus f of a, where the derivative of this big function is f of x. In other words, big F of x is an antiderivative. That's what we've been doing before integration. So we're going to find a new function, this big F, which happens to be the antiderivative of this function here. Then we're going to substitute the two numbers in and subtract, and that's going to give us the area. Okay, this is a pretty grand theorem. I'm not getting into the details of that theorem. Just let me show you what the proof looks like. So if you go to Wikipedia and look at the fundamental theorem of calculus, it's got some really good stuff here. But it gets into stuff to do with limits, which we don't deal with in the AS course. So if I just scroll through here, you can see that the actual proof of the fundamental theorem gets a bit intense and might look a little bit scary. It's just important to know basically how you use it to find areas. Okay, so there's some stuff here on limits and other things that you just don't need to know for the AS course. So if you want to get some more detail on the fundamental theorem, I suggest you talk to your teacher or have a look at Wikipedia, find out some more stuff on that. So here's the first example of finding an area under a curve. In this case we've just got a straight line, y equals 2x. We want to find the area between x equals 1 and x equals 4. Okay, so this is definite integration now. When we have numbers here with the integral, it's called a definite integral. So the area is the integral from 4 to 1 of the function 2x dx. Remember, this dx here is kind of saying we're doing it with respect to the variable x. It has more meaning than that. If you go back to the original kind of definitions and talk to your teacher about that. Okay, so we want an antiderivative of 2x. So we want to integrate, in other words. So add 1 to the power, divide by the new number. So 2x squared divided by 2 gives us just x squared. So x squared is the antiderivative. And as the formula we saw above, what we do is we substitute 4 into this antiderivative, minus, then we substitute 1 in. 16 minus 1 is 15 units squared. Okay, so that area is exactly 15 there. Now we could also, just to check that, work this out as the area of a trapezium. Here we've got a trapezium kind of lying on its side. The lengths of the two parallel sides are 2 and 8. The distance between the parallel sides is 3. So using the formula for the area of a trapezium, we also get 15 units squared, just to check that that's right. The good thing about this formula is that it works for curves as well. That's really helpful. So here's an example where we've got a curve, x minus 1 cubed. You can see it's like the x cubed shifted across to the right 1 unit. And I want to know the area between the curve, the x-axis, and x equals 0 and x equals 3. So you can see I've shaded the area here. It's just really important to note that when you're using these formulas to find the areas, that areas underneath the x-axis will come out as negative. So if I use the formula, work out the area from 1 to 0, which I'm going to do, the value you get out is negative. Okay, but clearly the area is positive. You can't have a negative area. Okay, so to calculate this area, what I'm going to do is work out the area between 3 and 1, then the area from 1 to 0. Okay, here's the calculations. x minus 1 cubed, so this is the reverse chain rule. Add 1 to the power, divide by the new number, times by 1 over the number in front of the x, which is just a 1, so it makes it easy. So here's the antiderivative. We substitute 3 in here, minus, then we substitute 1 in here. That gives us 4. So that is area here is exactly 4. I do the same thing between 1 and 0, same antiderivative, and I get minus a quarter. So clearly the total area there is 4 and a quarter. Okay, so that actual area there is a quarter. So 4 and a quarter is the answer. Here's two really cool questions because they involve infinite kind of limits going on here. So this first one is just the integral between 1 and 0. Now the reason this is infinite is this curve here never touches the y-axis. So this curve goes up forever, ever and ever. Never touches. So you'd think that this area that I've shaded here is infinite, but it isn't. If we use the calculus here, do the antiderivative of x to the minus a half, add 1 to the power, divide by the new number, that's 2 root x, substitute 1, substitute 0 and subtract, we get 2. That area there is exactly 2. Second example, we've got the integral from infinity to 1. So once again, looks like it should be infinite because this goes on and on and on forever. The curve here never touches the axis. So in this one here we've got a little bit of a tricky thing because we're going to kind of be substituting infinity, which is a little bit strange mathematically. So I do the integral, add 1 to the power, divide by the new number, tidy that up, that's negative 1 over x. Now I really can't substitute infinity into the formula, but what you can see when you do this, 1 over a really, really huge number is really close to 0. So 1 over 10 billion, 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 billion. If you want to put that out on your calculator, you'll see that that number is very, very close to 0. So this thing here, we're just going to say is 0. Minus minus 1 is just 1. So that area there is exactly 1. So how do we handle examples where we want to find the area between the curve and the y-axis? Well, the simplest way to do that I know is just look at the geometry of the situation and use the area between the curve and the x-axis to get the answer. So I want this orange shaded area here, the area between the curve 2 root x plus 1 and the lines y equals 3 and y equals 5. So the way I'm going to do that is work out the area between the curve and the x-axis, that's this green bit here, and the rest here are just rectangles, so that I can work out this orange part just by subtracting. So let's have a look at the working. I've done the integration here. I'm not going to go through the details, but I get this integral right here between 4 and 1 on the x-axis, and I've got that 4 and 1 just by looking at when y equals 5, what would the value of x be? That answer is 4. When y is equal to 3, what's the value of x? And the answer to that is 1. So substituting in, I find that that area, the green area there, is 12 1/3. So the area of the shape that we're looking for is just the area of this whole rectangle here, which is just 4 times 5, minus off the green area, 12 1/3, and minus off the area of this blue rectangle, which is just 3 times 1. Okay. Hopefully you can see that doing that will give us the orange area, which is 4 2/3. I think that's the easiest way to handle these kind of questions if you're asked to find an area between the curve and the y-axis. Okay, last important idea is to work out the area between two curves. This is very, very simple. All we have to do is, it's the same idea with the integral, is we just have to subtract the two equations. And sometimes it's easier to subtract the equations and simplify this bit here algebraically first before you do the integration. Okay. The important thing to note in this is that f of x is the function that's on top of. So if you're looking at the curves, it's the one that's above the other one. Okay. So let's look at this one. We've got 4 root x and y equals x. So there's the diagram. You can see 4 root x is the curved shape and y equals x is the straight line. So we want to work out that area. So the area is just the integral 4 root x minus x. We also need to find the x values. So one thing we need to do is find when 4 root x is equal to x. Okay. So that's going to be by squaring both sides we get this, and that gives us 0 or 16. So I know that 0 and 16 are the points of intersection, so we're going to need those. Okay, so go through the integration process, add 1 to the power, divide by the new number for both of these, tidy them up, substitute 16 in, substitute 0 in, and that gives me 42 and 2/3.